In this video, we're going to calculate the Jeffreys prior for parameter that is a parameter vector. So we're going to focus on this Fisher information matrix at first. But now remember, we have a computationally more friendly version that works in many common situations, and so we will actually use number 2 here when we calculate the components of the Fisher information matrix. And then from there, we'll use the formula for the Jeffreys prior in the case where we have a parameter that's a vector. And so we'll calculate that determinant of the Fisher information matrix and then raise that to the 1/2 power. So let's see how that works. Here we have an example where the data, let's start there, is a normal random variable which depends on the mean and the variance, and we're assuming in this case that both of those values are unknown to us. So therein lies the source of our parameter vector, which you can see up here. So theta is a vector with 2 components, mu and sigma, and so we want to determine the Jeffreys prior for this situation. So first we need to use that formula, which hopefully at this point we're all familiar with, which is the formula for the PDF of a normal distribution. But remember, for this calculation, we're regarding the x as given or constant and the variables as the mu and the sigma. So we're going to regard this as a likelihood function and not a density. Now we need to calculate the log likelihood. And so notice that if we take the log of the likelihood function and use the log properties, we'll get essentially that the log likelihood is a log of some constant. This constant is really 1 over the square root of 2 pi. And then minus the log of sigma, and since that's in the denominator, and that's a log property we should all be familiar with. And then this last part doesn't have a log in front of it because it had the exponential, and the log and the exponential cancel each other out. So that's all stuff that we should know. Now let's compute the partial derivatives, and we're going to have to look at the second derivatives of all orders. So let's start with the derivative of the log likelihood with respect to mu, and this is just an exercise in partial differentiation, and so that's something you'll just do with, you have to just do it with pencil and paper yourself. And then the second derivative of the log likelihood with respect to mu is -1 over sigma squared, as you see there. And then you can do the mixed partials either way, and you should get what we have there. And then finally, we need to start with the partial with respect to sigma, and then also look at the second partial both times with respect to sigma, and we get this here. Okay, so now remember, we've got to put together the Fisher information matrix, which I've got here. So since we have a vector parameter with 2 components, the Fisher information matrix is going to be a 2 by 2. And you can see that I've written these parameters for each row and for each column, because that kind of gives you an easy way to see which second partial goes where. And if we look at this, it looks like it's whatever the column you're in, that partial is the first one, and then whatever row you're in, that's the second partial. So like in this second row, second column, that's going to be with respect to sigma both times. And then the second row, first column would be with respect to mu first, and then with respect to sigma. So if we take all those expressions that we had earlier, and if you remember, the formula for the Fisher information matrix has a negative in front, then we just substitute in all the values that we got before, and notice that since we're about to take the expectation component wise, notice that in the second row, second column, when we take the expected value of this one, then that's just going to be sigma squared. And so then once you apply the expectation operator to each one of these, for each component, then you get what we have here, and which simplifies to this. So there is our Fisher information matrix. Now we need to calculate its determinant. Well, that's easy to, in this case. We'll just do the product down this diagonal, minus, and then do the product along that diagonal. So it just ends up being 2 times sigma to the -4. And then once you get the determinant, then that to the 1/2 power gives what we have here. And notice that this is an improper prior, since if we integrate, now again we're integrating over 2 variables here, so we've got to integrate as sigma goes from 0 to infinity, and then mu over the whole real line, and that gives infinity. So we can just take our Jeffreys prior to be 1 over sigma squared.